7.5 Improper integrals. Until now, we have been finding integrals of continuous functions over closed intervals. Sometimes we can find integrals for functions where the function of the limits function or the limits are infinite. These are called improper integrals. There are two types of improper integrals. One, either your A, which is your lower limit, or your B, which is your upper limit, is infinity or negative, positive or negative infinity. And the second type, or both, it could be from negative infinity to positive infinity, so they both could be that. And then the second type is where there is an infinite discontinuity in your closed interval AB that they're asking you to integrate. So let's go ahead and, I know that we did this one in class, this very first one, but I'm going to go ahead and do it again. We were talking about sketching this function, and we talked about from 1 to some t, and we talked about how that would be this region. And we said that we would have looked at this as the integral from 1 to t of x to the negative 2 dx, and that would have been x to the negative 1 divided by negative 1, which is also the same thing as multiplication by negative 1. So I can just put it out front there from 1 to t, giving us negative 1 over t minus a negative 1. And so that gave us negative 1 over t plus 1. And so what does that tell us about the value of our a of t? It's always going to be, since t is getting large, well, t could be anything. So this is going to be a small fraction. 1 minus that, so as t goes to infinity, the limit is 1, just by looking at that value. And now they want us to find in part C the limit as t approaches infinity of a of t. So for that, we would just say limit as t goes to infinity of our integral from 1 to t, 1 over x squared dx. And that's going to be limit as t goes to infinity. And we already found that this is going to be negative 1 over t plus 1. And as t goes to infinity, of course, this value goes to 0. And so our limit would be 1. So case 1 and 2, the improper integral converges if the limit exists. Otherwise, the improper integral diverges. Case 3, this improper integral requires both of the integrals to be convergent in order for the integral to also be convergent. If either of the two integrals is divergent, then so is this integral. So when you're splitting it up into, if you've got that case 3 where, I don't know, even if it's for case 3, even if it's going from, like 1 to 5, and it's 1 over, let's say, x minus 2 dx. You know that in between 1 and 5, there is a vertical asymptote. So anytime you're splitting it up like that, and you end up having two different integrals, if one of them diverges, then the whole thing diverges. Okay, that's what they're talking about there. And it says helpful hints. Remember that evaluating an improper integral is really two problems. It is an integral problem and a limit problem. It is best to evaluate them separately. And when breaking down improper integrals, be sure each integral is improper at only one place. That one place should be either the lower limit of integration or the upper limit of integration. So if your situation is like this, and you're going from 0 to 1, and let's say it was just that 1 over x dx, you know that this area is what you're looking for. So your a is what's going to be your limit, because that's the part has the it doesn't have a value, right? That's where your vertical asymptote is. So when you're writing your limit, I always write it, if it's the bottom one, I call it a. If it's the top one, I call it b. So I'm going to be approaching 0 from the right on this one if I was doing this problem, this little sample problem over here. So imagine that, even though it's weird because that's your bottom one. Oops, I forgot to put my integral in there. Sorry. So it would have been from a to 1. But it's like you're coming in from the right because that is your area. Had it been, like -1 to 0 on something like that, you would have been coming in from your left, okay? And that would have been, if it would have been -1 to 0, -1 to 0, 1 over x dx, and we would have said, well, this time it's my b that's at my vertical asymptote. So I'm going to say the limit as b goes to 0. So you're actually approaching this number, but this time you're approaching it from the left. Integral from -1 to b, 1 over x dx. Okay, and always do your integral first, get that answer, and then do your limit. All right, so now let's look at example number 2. This one is integral from 1 to infinity, 1 over x dx. We don't have to worry about the vertical asymptote here, but we do have to worry about infinity. So that's our other type of improper integral, is when we have either infinity or negative infinity in one of our limits. So we're going to say, lower limit or upper limit. So we're going to say the limit, and since my infinity is in the upper one, it's b, because I think of it as, the integral from a to b. So if it's my top one, I always call it b, and I'm going to be approaching infinity, because that's what that value is. See, just like over here, we were approaching 0, but we had to say whether it was from the left or the right. Here, if you're approaching infinity, it's fine to just put infinity. So we've got the limit as b goes to infinity, integral from 1 to b of 1 over x dx. And so we've got our limit as b goes to infinity of ln x from 1 to b. Limit as b goes to infinity of ln. I don't have to put absolute value because I know I'm going to stay on that positive side. ln b minus ln 1. And ln 1, we know, goes to 0. So this becomes the limit as b goes to infinity of ln b. And of course, as the natural log function goes to infinity, the y values go to infinity. So therefore, this one diverges. And by the way, on your homework, it is going to ask you to put the answer and whether it converges or diverges. So even though it didn't ask you specifically to do that in your notes, we should do that for each one of these problems. Okay, so on to our next one. So it has a little theorem here. The integral from 1 to infinity of 1 over x to the p is convergent when, and this would be p is greater than 1, and it is divergent when p is less than or equal to 1. And of course, this one actually means this. Okay? That actually means this, because p would have to be positive. And sorry, there shouldn't be an equal to sign there. Okay.